So this will be mini lecture 20, and we want to continue the discussion on first order circuit that are source free, zero input. And what I'm hoping at this point, we're going to define some of those. What does that mean to say first order circuit? We're going to do a little recap. And I want to use an example to kind of bring you along how we solve this. Today, my example will involve an inductor. Would also involve, we're going to do it using mesh, because we did some example before using nodal. So we're going to do some example using mesh. It's the same process, essentially bringing in the energy storage element voltage current relationship into mesh, just like we did for nodal. So let's do a little recap. Some of those terms we're using: first order circuit, source free or zero input. What does that mean? I'm going to try to link up a little bit to your differential equation course. I think that's important. Many times students take the differential equation course and think it's a hump to do and nothing that we're going to use. And unfortunately, it actually shows up in many engineering content. So I think it's important for me to link this particular section to your differential equation course. So let us go to the document camera, hoping that the gods of the document camera will collaborate with us today. And then we'll do a little recap, and then I'm going to put a problem and then do the problems essentially by hand, so that you see my thought and I speak to it, you see my thought process, how I think you should look at these sort of things when you get a problem like this. So we are looking at, again, first order. Make sure that things are looking good. First order circuits. Source free, or sometimes called zero input. Okay. That's what we're looking at here. And we're going to do an example today with discussion. Okay, let's go back here and make sure that, again, the document camera stays with us here. So a few things to define that's important to define. What is first order circuit? That's an important thing to define. And when we say first order circuit, we're looking at a circuit with either one capacitor or one inductor. Okay, so we're talking about a circuit with a single energy storage element. Okay, energy storage element. All right. So we understand now that inductors and capacitors can store energies, can store and release energies. That's an important feature that they have that makes them really different from resistors. They are passive elements. You can kind of see how I'm kind of looping our conversation, just many things that we've done over the last lecture. They are passive elements. That means follow the passive sign convention. And when we talk about passive sign convention, we're talking about when we write the voltage current relationship, we need to essentially make sure the current is entering the positive terminal of the voltage. Okay, so that's important here. And of course, just to be complete here, okay, we're talking about these two elements here. Let's put an inductance here, a capacitance here, and then a voltage here. Let's say V1, and a current here, I2, V3, I4. And we're talking about, again, the relationship for the inductor here, and I'm purposely using different. For the inductor, essentially, is V1 of t is equal L di2, the current to the inductor. And for the capacitor, it is the current that's equal to capacitance times the derivative of the voltage as a function of time. Okay? So these are very important, obviously. This is what we bring these relationships into nodal and mesh to get a differential equations. We're going to talk about that shortly, but this is kind of I want to give you a nice recap from where we are to kind of position ourselves. When I do that next problem, I'll talk about it importantly here. So that's a nice first step here, saying what a first order here. So then the next thing we want to talk about here is source free or zero input. So we're looking at circuit like this. I'm going to give you two examples here, okay? And that has, let's say, one capacitor here, whole bunch of resistors and dependent sources, okay? And then we're looking at perhaps connected to either a current or a voltage source, and then you have at some time T naught. Okay, you essentially, what I'm showing you here is that this is the only independent source in the circuit. And at some time T naught, we've been basically looking at time T equals 0, T naught equals 0. This particular switch here, which is connected, opens up. Okay, so after T equals T naught, no independent source in the circuit. Okay? And we can essentially do something here for inductor just to be complete, because we now know that first order circuit means one inductor or one capacitor. So we can have the same situation here at some T naught, and then that source that connects there. Okay, so same thing here, this case here, all right? Either for here or for here, we're looking at a first order circuit, either one capacitor with resistors and dependent source or one inductor. And then the independent source gets disconnected at some time T naught. And that's, I should say, after T equals T naught. Could be 0, but it could be another time, okay? Just to be generic here, I'll put T some naught here. After that, essentially, the circuit has no independent sources. So the way these circuits work, essentially, so again, for T less than T naught, we have a DC circuit charging either the inductor or the capacitor or inductor. Okay, that's what we have. So before the switch open, basically everything is DC, because we're looking at here DC source. We're not looking at anything varying. DC source, same here, okay? So for T less than T naught, essentially until the switch opens up, we're looking at essentially the capacitor or the inductor is sitting into a constant circuit that is a constant source circuit, okay? Nothing is changing, all right? And then so when that is the case, obviously, then capacitor behaves like an open circuit because it lets no current through. And inductor behaves like a short, a wire, okay, for T less than 0. Okay, that's where we are right there, all right? And then, of course, at T equal T naught, switch open, okay? Disconnect the independent source. And then you have a circuit essentially that looks like this without the independent source connected, okay? So inductor or capacitor is back. And the reason that these elements are back, because that switch change caused a change in the circuit so that these derivatives are no longer zero. So for T is back for T greater than T naught. Okay. So when the switch open here, it forces a change in the circuits. And then you get a situation, you get a circuit that doesn't have a dependent source, that it's a source free, but the capacitor and inductor, the energy storage element is back, and we have to use nodal or mesh to get our first order differential equation. First order differential equation. Okay. So that gives you kind of a lay of the land. Of course, I'm going to put a problems and discuss these elements with you with a problem but I wanted to give you somewhat a very, very clear lay of the land. When we do that, the first order differential equation we're looking at here is something like that. That is the first order, which is an homogeneous. It's homogeneous because it has no independent source after T greater than T naught when the switch opened, okay? And so we basically now can just write the solution as x of t equal some constant a e to the minus lower at, okay, for t greater than T naught, okay? So that's, in essence, what I want you to be able to do once you come up with a differential equation using nodal or mesh. And we're going to practice that today with another problem here. This, you can really see this as an homogeneous differential equation. It maps very nicely to a source-free or zero input. Because it's source-free, that's why the right-hand side is not a non-zero. It's zero. So, and that really is the standard solution for your homogeneous first-order differential equation with constant coefficient. The last thing I want to say about this, when we write differential equation using mesh and nodal, we normalize such that the highest order derivative as a unit coefficient, okay? Obviously, pretty soon we're going to be doing second-order circuits, so we're going to have second-order differential equations. But for this particular case here, we're looking about just the first-order differential equation. So the first-order differential equation, essentially the highest order derivative as a unit coefficient. We'll use that as a good practice here. The other thing I want to mention again, this constant A, it 1 over A is called the time constant. Okay. That's something you should be aware of. It relates to how fast that exponent dies out. All right. So often in the online exercise, and many times if you look at circuit examples online, you're going to see people asking you for the time constant for a first order circuit. So it's 1 divided by. So once you get the differential equation here, you should be able to identify the time constant. So we're going to go ahead essentially and do a problem. I'm going to show you the problem. And then I'm going to step by step guide you through it using this kind of discussion that we have right now, essentially. And I'm hoping that was very helpful. So this is the problem that I want essentially us to focus on. I want to spend a little time talking about it before I go ahead and solving. Of course, you know, this is a problem I found in one of the online textbooks. So this is, but I think it's a good problem. And what I'm going to do here essentially is use mesh. I like these problems because it is clearly a first order circuit. It has only one energy storage element, and it has an inductor. We've solved a couple examples here with capacitors. So this having an inductor is a perfect example here. And I'm going to use this one to do mesh. So the way, so this problem essentially puts these resistor, but I'm going to use the values in terms of working up the solution using mesh. So when you see a circuit like that, again, keep in mind, I asked you to note the switch time action, the switch change action time. Okay. In this particular case, it's t equals 0. At t equals 0, the switch essentially goes from position 1 in the circuit, and it goes and basically moves to position 2. All right. So that's what I want you to think essentially. What happened? At what time does the switch change? And what? So if you have one switch, you should have 2 circuits. one before the switch and one after the switch. Okay, so I'm expecting that you understand that. And the circuit before the switch, we're going to discuss that, should be a DC circuit with no inductor and no capacitor. And we'll discuss in a little bit why when we solve this issue, this problem right now. So right now, all I want you to see, again, this problem gives us the answer. So that's a good check for how we're going to solve this thing here. The other thing also, again, if you look at this circuit here, before t equals 0, the circuit is connected to position 1. The switch is connected to position 1. All right. And after, at t equals 0, the switch moves to the position 2. So after t equals 0, we're looking at, if you look at the part of the circuit to the right, the circuit has no independent source. That current source is no longer connected to the circuit. All right. So you expect to have a first order source-free zero input circuit for t greater than 0. So it links to what we were talking about when I did that little bit recap review. So we're going to put that in practice. We're going to do mesh so that we show how is mesh progressing, just like we did it for nodal, and hopefully this will be a good example, and we'll do some other problems. So I'm going to go to the document camera, and I'm going to essentially duplicate that problem in the document camera so that we can essentially work on it. So give me a second here, and hopefully the document camera will cooperate this time. Okay, so this is what I did. I basically duplicated the problem here. And again, we're talking about the switch at t equals 0 move from position 1, and then it moves back to position 2, disconnecting this segment again from the right. And the current here was the current I. So I think the current I was this, and that's the current that the problem was asking. Okay, and typically what you say, essentially, you see the statement, the current for all time, or whatever that response for all time, that means for all time t. So we recognize, again, switch moves at t equals 0. Okay, so that means need one circuit for t less than 0, and another for t greater than 0. Okay, that's the first thing I want you to notice here, that because of that switch change, that means we have two different circuits. The circuits are not the same. So our first thing essentially is to solve for t less than 0. Okay, and for t less than 0, what do we have? We have the current source, 5 amp. We have that resistor, the 2. So the switch is connected. So the 7 ohm here is not connected. And then we have the inductor with its current. And then the 10 ohms and the 3 ohms. Okay. So that's the circuit we have. Okay. And then obviously this circuit has existed for a very, very, very long time. Very, very long time. Okay, so it's been DC. So until that switch move at t equals 0, this has been like that forever. So the inductor behaves like a short circuit, like a wire. So what we have really here is this. We have the 2 ohms. And then the inductor behaves like a wire. The 10 ohms. And then the 3 ohms. Okay. And then the current I is the current here. Okay. So that's the circuit that we actually have for t less than 0, because for t less than 0, we have a constant source. So the inductor sees no change in anything, so it behaves like just a straight wire. So that's the inductor, how it behaves. All right, so you can recognize that 10 ohm, that inductor short circuit the 10 ohm. What I mean by short circuit, it forces the voltage across the 10 ohm to be 0 because it's just a wire. So the 10 ohm essentially has no impact in this particular circuit. Okay, so what we essentially really have is the 5 amp, the 2 ohms, and the 3 ohms with the current I coming here. Okay, that's what we really have, because that inductor shorted here forces the voltage across the resistor to be 0. If the voltage across the resistor is 0, the current is also 0, so the resistor essentially sees no signal. You can also see it as the current takes the path of least resistance, and I try not to use that too much because that doesn't really explain. It's kind of a nice stay, but I think what I just told you earlier is more the reason why we say the current takes the path of the least resistance, and there is no resistance here, so it goes, the whole current goes here. So we get to here, and of course we can use current division to say 5 amp times 2 over 2 plus 3. So what do we have here? 10 over 5. So this is 10 over 5. So this is 2 amp. So that's the current for t less than or equal to 0. Okay. So that's, if I did my math correctly here, that's what we should have. Okay. So that's, we solved the circuit for t, again, less than or equal to 0. Okay. So one of the things I want to point out is for t less than or equal to 0, we have no differential equations. We have no inductor. And if we had a capacitor, we would have no capacitor also. We're looking about solving a circuit basically with sources and resistors, because it's when the switch moves that the inductor essentially wakes up, if you will, and acts like an inductor. If everything is constant, such is the case for t less than 0, then the circuit looks like the inductor looks like a wire, and we're looking at a DC circuit. So I hope that makes sense to you. And we're going to, again, see more examples, more tutorial to say. So now our focus is t greater than 0. So the circuit we have here, that switch moved from 1 to 2. So what do we got? We got the 7 ohm comes to play. We got the 0.15 Henry. So the inductor is there. And then we have the 10 ohms. And then the 3 ohm resistor. Okay. And so here, because I'm going to do mesh, I'm going to put my mesh current I here, and this is mesh current I1. Okay. So I put my 2 mesh current because I know the current to the inductor was the current I. So I put my mesh current here, and then I'm going to now put voltage on my passive element, just like I'm going to carry on a regular mesh problem to come up with the differential equation here. So let's put V1, V2 across the inductor, V3, and V4 here. Okay. So 2 meshes, I'm going to write 2 KVL equations. So here's my steps here. First step is KVL equations. Then I'm going to do Ohm's law. Then I'm going to write the inductor relationship and bring it in. So KVL equations, what do we have here? Mesh I1 minus V1 plus V3 plus V4 equals 0. Equation 1. Mesh I, V2 minus V3 equals 0. Equation 2. 2 KVL equation, 1 in each mesh. I don't have any current source in this particular problem, so I don't have to write source equations like I do generally in mesh. Okay. Then we go to Ohm's law. Again, for the time being, realize I'm leaving the inductor alone. Ohm's law meaning what? V1 is equal to minus 7I1, passive sign convention. Okay. Then I have V3 equal 10 times I1 minus I. And finally, V4 equal to 3 times I1. So you see me putting these lines because I want to separate the major component of the mesh procedure for you. KVL equations, Okay, we don't have source equations here. Then we do Ohm's law. I want you to put the Ohm's law. So this step will be KVL plus Ohm's law. Okay, so I'm going to basically put this Ohm's law into the KVL. I'm not touching the inductor yet. So equation 1 becomes minus V1, so 7I1, plus V3 plus 10I1 minus 10I, plus V4 plus 3I1 equals 0. I collect terms here. What do we have? 7, 10. So 20I1 minus 10I equals 0. That's my new equation 1. Equation 2, V2, that's the inductor voltage, minus V3 minus 10I1 plus 10I equals 0. So not much I can do with this. Okay, that's equation 3. Then now I bring in the inductor. And of course, you have to know the inductor relationship. You can't be guessing it. You can't be confused about it. The inductor relationship says what? V2 is equal to 0.15 di dt. The current to the inductor is I. Okay, so this is my new equation 2. So now I'm going to put, wherever I have V2, I'm going to put this. I'm going to replace V2 in all my, in equation 1 and 2, and then replace. So equation 1 doesn't change because there is no V2. Equation 2 becomes 0.15 di dt minus 10 I1 plus 10I equals 0. That's my new equation 2. And of course, equation 1 remains the same because it hasn't changed. Okay. So what do I do next now? So let me put equation 1 here. This is equation 1. I'm just going to rewrite it. It's 20I1 minus 10I equals 0. So that's equation 1, equation 2. I'm hoping at this point you realize you have two equations, two unknowns. Two equations, two unknown, and the unknowns are I1 and I. Okay. So what we're going to do essentially is solve for one parameter in one and substitute in the other one. Okay. So you don't want to solve for a parameter that's sitting inside of a derivative. You don't. So you want to solve for something like I could solve for I1 here and put it here, or I could solve for I1 here and use I1 here. Let me do that. So here I'm going to say I1 is what? Is 1/2 I. Okay. Just solving for I1 from equation 1, and then I'm going to use that in equation 2. Just get myself a little bit of room here. So when I do that in equation 2, what do I have? I have 0.5 di dt, okay, minus 10 I1, all right? So minus 5I, okay, plus 10I equals 0, okay? So this obviously the only thing I can, this becomes or di dt plus 5I equal. That's my differential equation right there. Okay. I haven't normalized it yet, but that's the only thing that I have to do is to normalize it. Okay. And if I did my stuff well, I normalize it and I get so that's my normalized differential equations. Okay. And that differential equation, I'm going to solve it with the initial condition of I at 0 is equal to 2, which came from this particular solution for t less than 0. Okay. So this shows you the process here. Again, the first thing I wanted to show you is that the inductor, because the switch action, because the switch move at t equals 0, afterward, the inductor is back in the circuit. So whereas previously to the switch action, we're looking at a circuit with DC sources. So nothing essentially was changing. So the inductor behaves like a wire. But we need to find the inductor current because that is our initial condition. Okay. So we find the inductor current. All right. Then for t greater than 0, once the switch moves, the inductor is back, and I carry on a regular mesh approach to that. Okay. We don't have any source equation, any current source, so I don't have to deal with either source equation or super mesh. This is two essentially regular mesh KVL that I do here. So I put my voltage on my passive elements, two mesh currents, make sure passive sign conventions are followed when I write Ohm's law. So I do Ohm's law for all my resistors. I use the Ohm's law into the KVL, collect terms, and then I bring in the inductor relationship after that. So I then bring in the inductor relationship into those two equations, and then I use substitution to get a differential equations, which eventually leads me this to the normalized system. So the solution to this is obviously some constant C1 e to the minus 33.33 t for t greater than or equal to 0. Okay. That's the solution to this, where the value of C1 is going to be enforced at t equals 0. So C1 is going to be 2. Okay, so C1 is going to be 2. Okay, so that's what we have here. And I'm running out a little bit of space here. Okay, let me just... Okay. So C1 is going to be equal to 2 because I enforce the initial condition. So this is a good show of what a standard problem, first order problem is. In this case, using mesh. In this case, having an inductor. And I'm hoping that kind of details helps you figure out how to proceed with this problem. And we'll do some more problems in the future. Thank you.